real matrices with positive entries. So today is going to be proofs, and then Tuesday is going to be consequences. So truth today, consequences on Tuesday. So suppose that you have matrices A and B. Suppose that they are real matrices of the same size. Then what we write is A greater than B. That's if the entries of A are bigger than the corresponding entries of B. That's simple enough, and that's for all ij. And I could just as well have made that less than sign into a less than or equal to, sorry, greater than or equal to sign. There it is. And then I just put a greater than or equal to there. Yeah. Now, what would have happened if I wanted to say that A is sort of bigger than B but not equal to B? This is a very strong sense of A being bigger than B because I'm requiring it to be bigger in every entry, right? So I would use a different symbol if I wanted to. And that different symbol would be the sort of precedes symbol. It looks like this. Okay, so A, actually this is a succeeds. A succeeds B. So it's sort of like a greater than sign, but where it's been sort of squished to a cusp instead of having an angle over there. Yeah. And that would be if A, this is if A is greater than or equal to B, and it's not equal to B, right? So the point is that greater than B, A greater than B is not the same thing as greater than or equal to and not equal to. That's the problem, right? So this is an A greater than or equal to B and A not equal to B. So what that means is that Aij, so that's i.e. Aij is greater than Bij for some ij, not all ij. I mean, it could be all ij, but the point is you only require at least one. Yeah, so just be careful that greater than is not the same thing as greater than or equal to and not equal to. That's the main thing to get from that. Okay. We're never going to use this. I'm not going to use this symbol, but I wanted to show you this just to emphasize that point. Okay, so for example, what does it mean for P to be greater than or equal? What does it mean for P to be greater than 0? P greater than 0 is the same thing as saying that it's entrywise positive. Right? This is not the same thing. I know we've written P greater than 0 before. I guess there's a question of what kind of 0 I would put there. But the way I've done this is the 0 matrix. And I think when we do positive definite, that sort of thing, positive semi-definite, positive definite, this would be a number 0 instead of a matrix 0. So technically those aren't the same notation, but on the board, there's no way. So on the board, I would write the 0 matrix. So in a book, I would write the 0 matrix as a bold-faced 0 of some sort. But the usual 0 would just be a regular good old number 0. Anyway, don't get those notions confused. Even though those notations, we will confuse them. But don't get the notions confused. This is positive. This is entry-wise positive, not positive semi-definite. Okay. And if I said greater than or equal to here, what would happen? What word would I have to change on the other side?
Non-negative.
I would write here non-negative instead. Thank you. Non-negative. Okay. This is probably the simplest definition we've seen in a long time. Okay, so here's Perron's theorem. So suppose that you have P, a matrix that's in, it's n by n. And let's suppose that P P is positive in this sense, entry-wise positive, then P has what's called a dominant eigenvalue. Lambda of P. And it satisfies some properties. Okay? You should think of this as being the biggest eigenvalue. So dominant is going to be basically biggest. Okay, so first of all, this eigenvalue is a positive number. So there's a whole bunch of zeros that are going to come up during this lecture. I mean, a whole bunch of different kinds of zeros, right? This one is a matrix. This one is a real number. Now, keep in mind that when one writes, so we have a real matrix. Its eigenvalues a priori needn't be real, right? So this lambda of P is a priori a complex number. But when I write that a complex number is bigger than 0, I mean it is real and it is bigger than 0. Okay, so this is shorthand for lambda of P is real and it's bigger than 0. And PV equals lambda of P, V. Well, okay, for some V, we know that, right? That we know, but what we don't know is that. That's the important point, that you can choose a positive eigenvector. Okay, 2. No. So it says that the algebraic multiplicity of this dominant eigenvalue is 1. Okay? Right now, and now the next, this little bit that I'm writing is supposed to apply to both 3 and 4. So this is for kappa. If that's an eigenvalue, it isn't the dominant eigenvalue. Okay, so for any other eigenvalue, what we know is that 3, its absolute value is less than the dominant eigenvalue. Remember, kappa is now a complex number, and it could genuinely be a complex number. It doesn't have to be real. But in absolute value, it's less than this real number, this positive real number. And 4, if you have py is equal to kappa y, what that says is that y is going to be an eigenvector with eigenvalue kappa. Well, now it says it's an eigenvector with eigenvalue kappa. Before it could have been 0. Then, in fact, y is not bigger than 0. And here's now another kind of 0. Right? So this is now a vector 0. Yeah, always make sure that you understand what kinds of zeros you're writing down. Okay, so that's the statement of the theorem. It's all about the sort of it's all about the spectrum of this operator. This operator with positive entries. Yes, Nicole.
Why would you write y is not? Oh, wait, no, it's because of the thing. That's why you write not greater than or equal to, because of the precedes thing where.
Yes, that's right. So, right.
You can't just write less than.
I can't just write less. I don't want to write less than, right? Because less than would say that all of the entries of y are actually negative, which is actually specifically what this says is not true. Because for y to be greater than 0, okay, how do I say this? If y is greater than 0, then negative y is less than 0. So what this says is that there is no eigenvector. The eigenvector that you have for kappa can't have all positive entries. But for the same reason, it can't have all negative entries. Because if it had all negative entries, I could take its negative and then it would have all positive entries, but it would still be an eigenvector. So in fact, the only way to express this is this way, to say that it's not greater than or equal to 0, which means that it has to have at least one strictly positive and at least one strictly negative entry. So the picture for that is that here, here's your positive. Here's greater than or equal to 0. Oh, bummer. So little chocolate. That's actually very bad news. And here is less than or equal to 0. And so the point is that y has to be in here somewhere. Yeah. Okay, so let's prove this today. So that's going to occupy the whole rest of the lecture is the proof of this. It's not bad, it's just there's a substantial number of things to prove, and each one of them might take only a few lines, but there's 4 of them. And, we'll learn some more things as the proof goes. This is not one of those proofs that just tells you, okay, it's true. It explains kind of what's going on with this structure. Okay, so proof. Let's set L of P. This is really the key definition. It's going to be lambda greater than or equal to 0. So this is non-negative real numbers lambda, such that P of x is greater than or equal to lambda x, or some lambda, for some x, non-negative x. Remember, this is a real number, 0. This is a vector 0. All right, so this says that we have some vector x with non-negative entries, and we are going to rescale it. We're saying that P of it is greater than or equal to lambda times it. Okay, so let's just think about what that means. Remember the simplex here? I want this to be visible here, so maybe I'll. This. Yeah, so we've got the simplex. So this is the simplex sigma, right? So this is sigma here, which is the standard n-1 simplex. So the point is that P sigma, what kind of object is P sigma? This is a linear transformation applied to a simplex.
It's still a simplex because it's a linear transformation?
So you'd like to say it's still a simplex, and if P has full rank, then it is still a simplex. We didn't make a hypothesis about P having full rank.
That's true, we didn't. Some shape.
So then what can happen to a simplex if it doesn't have full rank?
It becomes degenerate, either a line or a point?
Well, this one becomes either a line or a point, but 3 here is n.
So if the number of dimensions decreases, some number of the dimension collapse.
Yeah, some of the dimensions collapse. What happens when you collapse some of the dimensions on a simplex? What kind of object do you get? What is the image of a simplex under a linear transformation? Actually, we could take this as a definition.
I thought it would still be a simplex, but of lower dimension.
Well, you'd like to say it would be a simplex, but what would happen? So remember, you're going to take these points to some points, and they're going to be, by the way, points in this space, right? So P is n by n. So it's going to take these points to some points up in the positive orthant. How do I know they're in the positive orthant? It's because P is a positive matrix, right? So it's going to take these 3 points to 3 points that lie somewhere up here. And in general, it's going to take these n points to n points that lie somewhere up here. What am I then going to do? What's the image of this simplex under P? I'm fishing for something. And what would happen if I took, let's say, the line segment that goes from here to there? Where would that go? All right, so I've just got some 3 points up here. In general, I would have sort of n points up here. If I take the line segment.
But boundary points raise whatever go to boundaries, something like that?
Yeah, well, not necessarily. If I had, 5 points, it might look like this, or 6 points, it might look like this, right? Now I'm just going to take all these things.
That would define a hyperplane
What'd you say?
or a polyhedron.
It's going to be a polytope, right? The image of a simplex under a linear transformation is a polytope. We could take that as definition of polytope, right? Polytope is a convex hull of finitely many points. So the image of this convex set is convex, and it's also the convex hull of the images of these standard basis vectors. Yeah? We proved this in lecture, I don't know, 6 or 7 or something like that, right? So this is just some polytope. P sigma is going to be some polytope here. Okay? Now this is if the entries of P are big, the entries of P might be small instead, in which case the polytope kind of sits down here. Yeah? So now what are we thinking about here? Px is greater than or equal to lambda x for some x greater than or equal to 0. So if lambda is big, then what can you tell me about this, this P sigma? That means that P sigma, so what are we trying to do? We're trying to rescale, we're going to compare that to lambda times sigma itself. All right, so what can you tell me about P sigma with respect to lambda sigma if lambda is big? So we're going to take this simplex and we're going to scale it by a factor of lambda, right? If lambda is huge, then how does that sit with respect to P sigma?
It becomes large and far away from 0, but maybe that's not the answer you're looking for.
Yes, it is. Right, so P sigma is entirely under lambda sigma if I take lambda to be very big. Yeah? P sigma is some convex polytope. It's a bounded, closed, convex set. So if I scale this triangle by enough, it will be entirely above P sigma. Right, now look at the condition that I want. I want Px is greater than or equal to lambda x for some x greater than or equal to 0. Well, if lambda x is really huge, that can't happen. Yeah? In order for this to occur, lambda has to be not too big. That's what I'm trying to get here, right? So if lambda is very big, then P sigma is entirely under lambda times sigma. Right? There's two things you can do to sigma. You can apply P to it, or you can scale it by lambda. And if lambda is huge, then nothing in here is bigger than anything in here. Right? Nothing in P sigma can be bigger than anything in lambda sigma. Okay, that's the first thing. What happens if lambda is small? Now what can you tell me? It says that lambda sigma is sufficiently under P sigma, whatever that might mean. So sufficiently under and entirely under. So these are sort of heuristic just to help you get the geometry of what's going on here. We're going to be talking about this as a fair amount for the next, 15, 20 minutes or something like that. But I wanted you to get some geometric picture before we start. Okay, so what we're doing is we're comparing P sigma to the scaling of the simplex by lambda.
Can you elaborate on why we're talking about a simplex? I don't think I caught why we're talking about
the simplex. So if that's 1, 1, and 1, you will see very sure. So you want to know why we're talking about this, or that we are talking about a simplex?
like what? I don't understand how we went from L of P to a simplex. Like why that was a natural thing to do, or why we did that at all.
You'll see in about 30 seconds. Let me start the proof and you'll see. So here's a lemma, which I wanted to convince you of first. So L of P is compact, and it has it has some non-zero element in it. Right? So it's already by definition consisting of real numbers that are bigger than or equal to 0, and I'm saying that there is actually some non-zero positive number in there. So what that's saying is that some scalar multiple of this guy is going to have some vector that so let's see now. I want lambda x to be less than or equal to px, right? Well, okay, I'll draw another picture for that in a second. Let's just start the proof of this lemma. So if we have x in Rn, and if I know that if x is not 0, and x is greater than or equal to 0, that's the condition that I'm looking at over here, then what can you tell me about px? I claim that px is strictly positive. Why is that? Well, the entries of P, remember the hypothesis on P is that all of the entries of P are strictly positive numbers, right? So now if you give me a vector x that's not 0, but all of its entries are non-negative, that means at least one of them is strictly positive. That means that you've taken at least one of the columns of P with some non-zero positive number, non-zero positive coefficient, and that makes px bigger than 0. But you're taking a linear combination of the columns of P with coefficients that are non-negative, at least one of which is strictly positive. That means that this vector is bigger than 0. Okay? All of its entries are strictly positive. So P is doing something like, it starts off with your vectors like this, like these basis vectors, it starts off with those and collapses them at least somewhat as it sticks them in, right? It has to pull them off the boundary here. So it's a little bit contracting in that kind of way. Okay, so now, this would be promised, why are we looking at this simplex over here? Okay, this is for Garrett. So let's let 1 be the vector, just the vector of all 1s. This is actually a row vector of all 1s. Okay? So I can write 1x, whoops, that should say 1x is equal to x1, which is x1 plus xn. And that's because x is greater than or equal to 0, right? It should say absolute value of x1 plus absolute value of xn and so on. But the point is that x is greater than or equal to 0 here. Okay, this is just a notational trick at the moment. Where do I have the argument that says that? Right. So let me write this statement down. So px is greater than or equal to lambda x. That happens, that's if and only if the same is true for x over x1. So we may as well assume that we may as well assume that 1x is equal to 1. This is the reason, Garrett, why we're talking about the simplex. Because this condition is stable under replacing x with a scalar multiple, right? If I put 2x in here, p times 2x is greater than or equal to 2 lambda x if and only if px is greater than or equal to lambda x. So I might as well have rescaled x to assume that it lies in that simplex to begin with. Garrett, did that answer your question? Yeah, good.
Maybe it answers this question, but it raises one of my own, which is, I guess, why a simplex specifically then? Why not some other geometric shape?
Because I'm looking at the set of vectors that are greater than or equal to 0. And when I rescale the set of vectors that are greater than or equal to 0, I get all of the points in this simplex.
Oh, okay. Yes,
If I had chosen some other cone other than this one, then I'd get some other polytope over here. But I'm choosing the vector, I'm choosing the set of non-negative. It's because the simplex is the link at the origin of the positive, of the non-negative orthant. Whatever that, right? So the point is I've specified at the very beginning that I'm looking at non-negative orthants, because I'm looking at greater than or equal to 0 stuff. And so that way, when I rescale them, I end up with simplices like this.
We're
Yeah,
really
no,
looking
now I understand geometrically why the simplex is the choice at hand.
So we're
Yes.
looking at like the intersection of the first quadrant with the one norm, right?
Yeah, that's right.
Okay.
Yep. Okay. So back to the proof of this lemma. This is really a parenthetical comment that will come up in a few lines, but not yet. So now I'm going to make some of this a little bit more precise. So if lambda goes to 0 from the positive side, then in particular, lambda x goes to 0, right? Which implies that lambda x is less than epsilon times 1 transpose. That's the vector of all ones eventually. So what's the picture that's going on over here? The picture is that I've got one of two possible things happening. I can think of this, and I've got my x sitting over here. And then what I'm doing is I'm throwing on some, okay, so now where's px? Suppose that px is maybe over here. Okay? So that's my px. And the point is that now, let's look at the stuff. So what do I want? I want that px is greater than or equal to lambda x, right? So what's the stuff that's bigger than or equal to lambda x? Well, if I chose lambda really big, or just anywhere, right? So how about 1? How about lambda being 1, right? Then the stuff that's bigger than or equal to lambda x, that's this stuff. And px isn't in there, right? I want px to be in there. How do I force px to be in there? I just move this thing back along x until it contains px, right? So I can keep taking lambda smaller and smaller and smaller, and eventually I'll end up with px greater than or equal to lambda x, right? So this thing, that's lambda x. And so if I take lambda small enough, it's going to end up less than px. Why is that? And the proof here is very simple. It's because lambda x, it has small coordinates, right? All I want is that every coordinate of px is bigger than every coordinate of lambda x. Well, lambda x has, when I take lambda to get small, all of the coordinates of lambda x are very small. Some of them might even be 0, actually, right? Because x is greater than or equal to 0. Some of the coordinates of lambda x might be actually 0. But that's okay, because I just want it to be less than px. And px, we know, is strictly bigger than 0. So all of its coordinates are strictly positive. Fair enough? I'm trying to say there's not very much going on here. It's just, if I just written the symbols, it maybe wouldn't be so clear what's going on. But geometrically, this is a very simple thing that's happening. Okay, so let's finish this argument. That implies that lambda x is less than px. This I have to fix the, should say 1x somewhere. Yeah. And that implies that lambda is in LP. Eventually. And then eventually. So what's another way to say this, by the way? Another way to say this is that I'm going to draw the same picture again. Okay? There's my x, and there's my px, which is bigger than 0. And the point is that I've got this box. I can look at what's less than or equal to px. That's inside that box, right? And the point is that there's a lambda that's going to be there, right? This vector, x, when you scale it by enough, it eventually, so how do I say this? It starts off at 0, and then it sort of grows as it gets to x. And the point is starting off at 0 means that it's inside of this blue box. And so when I just go a little bit along x, it stays inside the box. Right? But I want lambda x to be less than or equal to px. That just means that when I start off the vector x, it stays inside of this box for at least a little while. It's the same as the argument over here, just kind of dual. Yeah, this is looking at the stuff that's bigger than lambda x. This is looking at the stuff that's less than px. Okay, so why is this thing bounded? Right, we have to show that it's compact. Set, we have to show that the set L of P is compact, so it has to be closed and bounded. So we'll show bounded first. Okay, so first we need L of P bounded. Okay, how's that going to go? Well, it comes down to, it's this thing. When lambda is sufficiently big, P sigma is entirely under lambda sigma, and so you can't take lambda too big. Okay, let's just make that precise. So we're going to use this at some point. Yeah, we're going to use that. So the point is that we're going to use that right now, right? So if I'm looking at the set of x's, which set of x's do I have to think of? Well, when you start, Garrett, this is going to be important for you. When you start, you're looking at all of the possible x's. But then you realize that because of this parenthetical comment, you only need the x's in this simplex. And that's a much simpler problem to consider. Because now, as I say, all you have to do is scale lambda enough so that it makes that simplex big with respect to P sigma. Okay, so let's make that precise. So I have that 1 px is greater than or equal to 1 lambda x, right? So px is greater than or equal to lambda x, right? Let's start with that. This inequality implies this inequality, right? So I'm looking at lambda inside of p, right? So lambda is p implies this, right? So that means I can put a 1 in front of both, and it's still true. Okay? Because this entry-wise, right? I'm just looking at the entries of these things. It's just summing up a bunch of entries. Okay? What is 1 lambda x? 1 lambda x is lambda 1x. Again, this is just properties of matrix multiplication, yeah? Lambda 1x. And that's the same thing as, what's lambda 1x? This is just lambda, right? And this thing, what we're doing is we're assuming that, that 1x equals 1 here, right? That's this thing over here. Okay. So now, let me take B, just to give another letter. Let's let that be the, let's take 1p. What is 1p, by the way? You have to think back to the definitions. 1 is the vector of all ones. It's the row vector of all ones. So when I multiply that by p, it's going to take the sum of the rows of p. Yeah? Okay? So this thing is the sum of the rows of P. Okay? So now let me take this thing to be the infinity norm of that. What's that otherwise known as? Infinity. It's the max entry of the sum of the rows of P. Okay, that's just some number. The point is this is some positive number, some strictly positive number. Okay? So if I do that, then this implies that, well, it implies this. It implies that, that B1x, right, this is less than or equal to B1x. Right? Because think, this is 1px. Right? This is 1px, and 1px, we're taking the maximum here. So b times 1x is certainly greater than or equal to 1px, because I'm just taking the maximum here. And that is equal to b. I know if I go too far left, you won't be able to see it on the screen. Can you guys still see this b online? Yes, okay, good. If I put it over here, just out of curiosity, can you see that? No, yeah, I didn't think so. Yeah, that's why I put it down there. Okay. Yeah, so what do we have here? The whole point of this little calculation, again, we already understand what's going on because we know that if we take lambda very big, then it's going to scale this so there can't be, because that won't, so the inequality won't work. But we've just made it precise by just saying that if you take B to be the maximum of the entries of the sum of the rows of P, then that B is big enough so that it has to be bigger than lambda. Right? It says B is greater than or equal to something is greater than or equal to something equals something equals lambda. That means that B is greater than or equal to lambda. So it says lambda in P, lambda in L of P, I'm sorry, implies that B is bigger than or equal to lambda, which means that it's bounded. That's all we needed. All we are doing is making precise the fact that it's bounded. No big deal. Okay, so why is it closed? It's closed because the simplex is closed. So we're going to use the fact that the simplex is closed to do the closedness of L of P. All right, so what are we trying to do? We're trying to sort of rescale this thing so that some vector in, let's see now, some vector in the scale of this is less than or equal to the corresponding vector in here. And so the point is that if I have a sequence of things, if I have a sequence of lambdas that work, and I'm going to get a sequence of vectors in here, and the sequence of vectors is going to have a convergent subsequence. That's what's going to happen. So suppose that I have a bunch of lambdas approaching, a bunch of lambda k approaching lambda with lambda k in L of P. That's what happens when you write with chalk. It's shorter than your thumbnail. Oh, much better. Okay, so you have a sequence of these things converging to lambda. What conclusion do I want to make? Yeah, I want lambda to be in L of P. Yeah? Okay. Okay, so what do we actually know? We know that there exists an xk, and that's going to be there exists an xk in sigma, right? Inside of this simplex here. I'll draw the sigma bigger. That's sigma, right? Sigma is the simplex, so this is the simplex sigma, right? 1x equals 1. So it's going to be an xk in sigma with P xk, and that's supposed to be greater than or equal to lambda k xk. That's purely the definition of lambda k being in L of P, right? It's just this. It says there exists some xk such that P of xk is greater than or equal to lambda k xk. That's purely the definition of lambda k lies in L of P, nothing else. Okay, and that's going to be true for all k, and you may, so yeah, that's true for all k, good. So now, if we look at the xk's, xk, such that k is in N, this has a convergent subsequence. Why does it have a convergent subsequence? So now we're looking at a bunch of x's that sit in here. Right? They can jump around. The lambdas converge, but we have no hypotheses on the x's. Yeah? But the x's are jumping around this sigma. What can you tell me about sigma?
Closed.
It's closed. It's not just, it's compact, right? It's closed and bounded, so it's compact. So every sequence in here has a convergent subsequence. So since sigma is compact, gosh, things I don't want to erase. I'm going to leave up the definition of L of P. I'm going to leave up the statement of the theorem and the definition of L of P, but I'm going to erase everything else. And the pictures, but I'm going to erase everything else. I need to keep pointing to these pictures.
Professor Miller, I have a question about that picture.
Sure, which one? There are three.
The one with sigma and the image P of sigma.
Yep.
Yeah, that one. You show like a polytope being P of sigma. Would that be, in this particular case where you just show the simplex in R3, wouldn't the image be, you know, like two-dimensional, just some subset of an affine?
Yes. Yes, it would. In this particular case, it would in fact be a simplex. Because when you have three vectors here, three vertices, a three-vertex polytope is either a triangle or it's a line segment. So yes, but I need to convey the n-dimensional picture more generally. If you remember when I drew this picture, what I did was first draw 3 points and then say, but in n dimensions we have more, and then I threw in more points. Yeah, is that it?
Yeah, that's it.
Yes, okay. But for your intuition, you should think of this thing, you should think of this as being a tetrahedron, and this as being, oh gosh, 4 dimensions. So yeah, with 4 vertices, you still only get simplices. So you have to think at least 5 vertices, so at least 4 dimensions, in order to get this thing to be not a simplex. In order to get this thing to be not a simplex. Yeah, I mean, do that, but the point is, well, don't use entirely your intuition from dimensions 1, 2, and 3, or even 4. You might need to go up to at least 5 before you see something interesting. This is fairly common in polyhedral combinatorics, that you have to go up to fairly high dimension. I mean, 5 is not very high, but higher than you'd like before you can actually see phenomena that occur. Okay. That's delineating the board that I'm allowed to use now. Okay, so we're going from here, right, all the way up to here. Okay, so this sequence is, so we have a convergent subsequence. So that means we can replace this sequence of lambdas, lambda k, such that k is in n, and the sequence xk, such that k is in n, by, so with subsequences, this word has 2 pronunciations in English. The subsequence, but it's also a subsequence. By the subsequence of this event and that event. With subsequences, to assume that in fact lambda k approaches lambda and xk approaches some x. Now, what can you tell me about this x? So this lambda we don't know about. We need lambda to be inside of L of P. That's what we're trying to conclude. What can you tell me about x, however? This is in sigma. Right? That's the key point, is that this x is now in sigma. Okay, thus, what can you tell me about the limit as k goes to infinity of the sequence that looks like P of xk is greater than or equal to lambda k xk. So we knew this to begin with, right? Pxk is greater than or equal to lambda k xk. That was true before we took any subsequences. However, now we know that that the x's converge to something, and the lambdas converge to something. So what can you tell me about this? What does Pxk converge to? Does it converge to anything? Why? I'm looking for a 3-word sentence. Why does Pxk converge to something? Okay, I'll take that as my 3 words as it is continuous. The it being P, right? Linear maps. So linear, I want to say homomorphisms are continuous. There we go. Maybe I should use 4 words and say linear maps are continuous. Yeah, but linear implies continuous is what I'm really looking for. P is linear, so it implies it's continuous, so it takes limits to limits. Now this is going to be P x is greater than or equal to lambda x. And now we're done. Or maybe I should really say, this implies that lambda is in L of P. And that's what we need. Okay. So there were details to check, but the two things that I wrote on the board, you know, the sort of the heuristic geometry, that's all we're doing is making that precise, right? We chose a specific bound to show how big you can take lambda to how big you. So if you take lambda that big, then you leave the L of P. Yeah. Okay. Okay, so this set, what was the claim? The claim has, the lemma has been erased, but what we were proving is that this set L of P is closed and bounded, right? It's compact. What can I do with compact sets?
Find maximum minimum.
I can, yes, so I've got the statement of the theorem here, so I need to be pointing at these things. That's why I left it up, right? So what do we have to do? We haven't proved any part of this theorem yet, right? We've just proved a lemma. So I need to tell you what lambda of P is. That's the idea, right? Lambda of P is supposed to be some real number, and let's set lambda of P is equal to the maximum of L of P. That's the reason why we need it to be closed and bounded. So now I can take a biggest one. So again, in terms of this picture, we're going to be rescaling this simplex by lambda. As we do that, it's going to sort of be passing through P sigma, right? Now, as you're passing through P sigma, you're looking at these kind of phenomena, and you're saying, okay, well now, you know, you're looking at some vector here, x, right? And you're taking lambda x, and you want it to be less than or equal to px. Well, when you scale it far enough, it's going to not work anymore, right? So the set of x's, the set of px's that work is shrinking as you make this thing get bigger. And the point is that there's a last point at which there's a biggest scale at which there's still a px that works. And the point is it's going to be a unique one. And that's going to be this v that we're looking for. Okay, so you're sort of scaling this up. And as you do so, it passes through this polytope. Well, as it's passing through this polytope, it's expanding. So fewer and fewer of these guys have scalar multiples that are beneath them in this simplex. To the point where when you pass the simplex all the way through, of course, none of these guys have scalar multiples that are beneath them because the simplex is entirely above it. Okay, so this is the, right? Lambda P is the maximum of this L of P. So here's a claim. And the claim is that lambda of P is actually an eigenvalue of P. In fact, if you have that PV is just greater than or equal to lambda of P, V, and we know, by the way, that since lambda of P is in there, there is such a V, right? Lambda of P lies in L of P, so there is a vector V such that P of V is greater than or equal to lambda of P times V. Right? There is such a vector V, and I claim that it's unique. Well, we don't know that yet, but for V greater than or equal to 0, this implies that in fact PV is equal to lambda of P, V. So what it's saying is that as you pass this simplex through, there's going to be a point at which there's exactly one vector in this set that's going to equal its scalar multiple that's in the scalar multiple of this set. So you're really scaling this thing so that it intersects this thing, and there's going to be one vector, exactly one vector in the intersection that's going to be where this vector is greater than, well, where they're equal, right? Where the lambda v is going to be equal to the PV. you want me to leave these pictures up on the board? If I have to redraw one of those, it's actually not so bad. The other ones are a little bit harder to reconstruct. These are very simple, they're just sort of straight line. Okay, so proof. So proof of the claim. So suppose that lambda is in L of P. This is any lambda. So what does that mean? It means that PV is greater than or equal to lambda V for some V greater than or equal to 0. This should be greater than or equal to, not greater. I don't think it matters. Okay, so PV, what happens when PV is not equal to lambda V? So what I want is that this, so what we want here I want is that this implies that lambda is not equal to lambda of P. So there's two choices, right? We know that PV is greater than or equal to lambda V. So there's only two choices. Either PV is equal to lambda V, or PV is not equal to lambda V. That's true for all lambda in L, of P, right? Whenever you have the V such that PV is greater than or equal to lambda V, there's two choices. Either you get an equality sign or you don't. What I want to show is that if PV is not equal to lambda V, then you don't have lambda of P, which means that when you have lambda of P, you have to have equality. Yeah? Okay. So I want to conclude from this, so PV not equal to lambda V, I want to conclude that lambda is not lambda of P. That's what I want to conclude. I want to prove that lambda is not maximal in L of P. Okay, so I can make lambda a little bit bigger, it still stays inside of L of P. Okay, oh, not again. Okay, so 0 is not equal to PV minus lambda V. Okay, well, we understand that. Let me call this W, okay? So W stands for witness. It's the witness to the fact that PV is not equal to lambda V. I just made that up, but whatever, it works. It implies that, okay, so epsilon PW is greater than 0, and that's going to be true for all epsilon greater than 0. Why is that? I don't want this to be P sub W, I want P times W. What can you tell me about W? Well, PV is greater than or equal to lambda V, right? So if I take PV minus lambda V, then this thing is greater than or equal to 0. Yeah? And that means that P of it is strictly positive, which means that epsilon P of it is strictly positive. Fair enough? Yeah. This whole thing is filled with details that line by line, they're very easy to verify. When you step back, you're like, how did you what, huh? But every line is very easy to verify. Okay. And that's since P is strictly positive. Okay, that means that P of V plus epsilon W, what's that? That's P V plus epsilon PW. Remember the definition of linear transformation? There it is. Remember in 221 when you saw this for the first time? This is the definition of linear transformation. P of V plus epsilon W is PV plus epsilon PW. Okay, and that I claim is greater than PV. Right, because epsilon PW is greater than 0. So this is greater than PV. What's PV? PV is lambda V plus W, right? PV, W is PV minus lambda V. So PV is W plus lambda V. Yeah? And that is, so I'm going to rewrite this last line over here. So what's the last line there say? The last line there says, great, can you read it out to me? It says greater than. Okay, good. Okay, and that, so lambda V plus W is, I claim, greater than or equal to lambda V plus epsilon lambda W. And that's for epsilon less than or equal to 1 over lambda. Yeah? But that's equal to lambda times V plus epsilon W. Okay. That was a little trick. So what we've managed to do is we've managed to add something to V, this epsilon W, right? We took this witness, here's a witness to PV being bigger than lambda V. And what we did was we added on some little tiny multiple of this witness to V itself. Right? What that does is it moves V up a little bit, but it's going to have this property that we can multiply, that it's going to play well with L of P. What's going to happen? Okay, so if we take X to be V plus epsilon W, that's this one over here, then what we get is that Px is greater than lambda x. Here it is. This is Px. There is a greater than sign right there. Right? There's my greater than sign. And here's lambda x. Fair enough? Okay, so now you just do something standard. So when you have Px is greater than lambda x, that means it's greater than or equal to lambda prime x, where lambda prime is slightly bigger than lambda. Yeah, if you increase, so if you're making x, something, this says greater than, the greater than here means coordinate-wise, all of them are greater than, so you can increase lambda by a little bit and it'll still be true. Okay, so this says that Px is greater than or equal to lambda, I could put a greater than actually, it would still be true, but greater than or equal to lambda prime x for any lambda prime that's bigger than lambda with, as long as lambda prime minus lambda is sufficiently small. Yeah, so I can just bump up lambda just a little bit. And this implies that lambda is not equal to the maximum inside of lambda P. Yeah? So what did we just do? There's a picture, by the way, in the notes that I do not want to copy on the board now. It will take a long time. I don't want to do it. But what we did is we used this witness to PV being bigger than lambda V. We modified V by adding a small multiple of this witness, and that gave us a vector that witnessed the fact that lambda is in fact not maximal. It tells you in which direction you should move to make lambda bigger. Yeah, so the witness tells you what direction you should move to make lambda bigger, which will allow a bigger choice of lambda. Okay. Then I need to finish the proof of one. So the main point here is that we set lambda of P to be the maximum of L of P. And we have this claim that says that lambda is an eigenvalue. And in fact, if you want to say what's an eigenvector, what's the eigenvector look like, it's, all you have to know is that for this particular choice of lambda, as soon as you have this greater than or equal to, then you have equality. That's nice. So lambda of p is it's an eigenvalue of p, implies that PV is actually lambda of p, v, that's for some non-zero v greater than or equal to 0, and that implies that, because p is bigger than 0 again, that lambda of p v is bigger than 0, and that implies that lambda, and that's because, again, lambda of p is itself bigger than 0, and that implies that v itself is bigger than 0. Right. Okay. All right, so that's one. Right? So the point was, again, this says that if PV is greater than or equal to lambda PV for V greater than or equal to 0, yeah, lambda of P automatically has such a V. There is going to be a V such that PV is greater than or equal to lambda P times V. Yeah? That's because lambda of P is an element of L of P. Right? That means there exists some X here. And this claim says that as soon as you found that V, in fact, V is an eigenvector. But I needed to know that not just that V is greater than or equal to 0, but that V is actually greater than 0. How do I know that V is greater than 0? Well, PV, this has strictly positive coordinates. So if this has strictly positive coordinates and it's a scalar multiple of V, then V itself has strictly positive coordinates too. That's all that last line over there says. Good. That's number one. Now I can erase this big long line here since it's not actually a continuation now. Now we're going on to number two. Number two. We need to know that the algebraic multiplicity is 1. I'm going to first check that the geometric multiplicity is 1. Okay? G of lambda P is 1. Well, I want to check that. So suppose that we have W that's in the eigenspace of lambda of P, and suppose that it's independent of V. Okay, so now we have V, and so we have our V, by the way, right? We've got our V. Number one says we have our V. I'm going to take that V. I might as well even assume, I don't know if I need it, but let's assume that V has one norm 1. So it's in the simplex. I don't have to, but I can, right? I don't think I'm going to need it either, but if I do need it, then I'll just use it. Okay, so if I have another W, this is not the same as that W. This is just another W. It's another eigenvector with eigenvalue lambda of P. If it's independent, then the line, this is fun. The line VW, so the line connecting V to W, this thing has to exit R to the n plus. It has to do it somewhere, right? What that means is that, sort of one coordinate of V is bigger than some other coordinate of W, and one coordinate of W is bigger than the corresponding coordinate of V. So when you add, a big multiple of one to the other, it's going to make a sign switch. When a sign switches, leave the positive orthant. Okay, so when it exits Rn plus, this implies that if I look at the eigenspace of lambda of P, then it says that the intersection with the boundary of the positive orthant, take away 0, How do I know I don't get 0, by the way, when I take this line? Because they're linearly independent. I can't get 0 from a linear combination of V and W. Right, isn't that nice? Is non-empty. And that's a contradiction. What does it contradict? It contradicts this. Right? What we just showed, this line, exactly what it shows is that if you have a non-negative vector that's an eigenvector, then that non-negative vector is automatically positive. If every non-negative vector that's an eigenvector is automatically positive, then you can't have any eigenvectors that are on the boundary of the positive orthant, which means that you have to have only one direction of eigenvectors. Okay. That's G of lambda, though, not A of lambda. So for A of lambda equals, A of lambda of P equals 1. What we need is that we need there to be no vector y in R to the n with py is equal to lambda of py plus alpha v. Why do we need this? Why is this the condition?
Generalized eigenvector.
This is generalized eigenvector stuff, right? This is the condition that says that p minus lambda of p applied to y is a scalar multiple of v. So that's the condition that y be the next vector up in a generalized eigenbasis. That alpha, I want it to be positive. So I can replace y with negative y, right? So I can assume that alpha is bigger than 0. Yeah. And if I replace y with y plus beta times v, remember, all I care is that I get some multiple of v at the end. If I change y by adding a multiple of v, it's not going to change the fact of this statement, right? This is a statement about the span of y and v, not about y itself. So I can move y around by adding multiples of v at will and not change anything about this. Okay? So I can assume that y itself is bigger than 0. And the reason for that is just that, if I have this picture that looks like this, and if I've got my v here, and if my y is down here, then if I add enough v to it, then I end up inside the positive orthant. It's just because v has strictly positive coordinates, right? If I add a big multiple of something with strictly positive coordinates to y, eventually it will have strictly positive coordinates too. This is not a deep statement. Okay, so now we have this equation, star. So star, together with the fact that v is bigger than 0, implies that py is greater than lambda of p, y, right? This is lambda py plus something positive. Fair enough? And that implies, by the same argument, that py is greater than or equal to, or greater than, doesn't matter, lambda prime p, lambda prime, what did I just do? Py is greater than lambda py.
You can make lambda a little bigger since it's.
Yeah, it's going to be, I'm puzzling at the parentheses that I wrote in my notes, which just seem to be incorrect. For any lambda prime bigger than lambda of p with lambda prime minus lambda of p, as long as that's sufficiently small. So I need to circle this weirdness in my notes.
Should we have the P there?
Yeah, I don't think the P should be there on the right hand side.
Just a second. Py is greater than lambda py. This implies that that one is missing. Yes. Yeah. And that's a contradiction, right? This is the contradiction. Contradiction is that you have that you've got a lambda prime that's bigger than lambda of p, and it still satisfies this equation, this inequality. Yeah? You're not allowed to have this. I should make that equals, just so you can pattern match with this thing. Right? So we found a lambda prime that's in L of p, and lambda prime is bigger than lambda of p, which is not possible.
So,
Yeah.
did we need the geometric form? Or was it for the geometric multiple, so use one?
Yes, because I needed to know there's just one v here. This is the v that works. Yeah. It needs to be just that v. Yeah. Okay, we'll do number 3 next time.